Welcome to solverfy.
Question 105 is a buffer solution calculation. For buffer solution calculations, we typically use the Henderson-Hasselbalch equation. However, this question is a little different in that it gives you concentrations associated with one buffer for which you need to calculate the pH, and then knowing the pH of that one buffer, calculate the concentrations of the other species needed for a different buffer. So we know the concentrations exactly for the second buffer. So let's calculate the concentrations for the second, or let's calculate the pH that is created from the concentrations of the second buffer, and then we can use that pH of the second buffer to calculate the concentrations required to achieve that same pH of the first buffer. So the second buffer is comprised of benzoic acid and some sodium hydroxide. So we need to know, when using the Henderson-Hasselbalch equation, the Ka value for benzoic acid. The Henderson-Hasselbalch equation is pH equals pKa, which is the negative log of the Ka for the weak acid in the buffer, which is benzoic acid, plus the log of the moles of base over the moles of acid. The moles of base will be defined by the moles of strong base added. Every time we add a mole of sodium hydroxide to a solution that contains benzoic acid, 1 mole of benzoic acid is consumed, and 1 mole of benzoate, its conjugate base, is formed. So because we added 25 milliliters of 2 molar sodium hydroxide, then if we take 25 milliliters, 0.025 liters, multiplied by the molarity of the sodium hydroxide, this will give us the moles of sodium hydroxide added, which will now be the moles of benzoate, the weak base formed. The moles of weak acid that will be present will be the volume of the benzoic acid solution, 475 milliliters or 0.475 liters, multiplied by the concentration of the benzoic acid. This is the original moles of benzoic acid before adding the sodium hydroxide, but when we add the sodium hydroxide, the moles of benzoate formed will be equal to the moles of benzoic acid that was decreased. So now we have pH equal to pKa plus the log of the moles of the weak base that are present divided by the moles of the weak acid that are present after adding the sodium hydroxide, and we get a pH of 4.246. So now, to determine the concentrations that are required for the first buffer in order to achieve the pH of that second buffer, which is 4.246, we need to take the negative log of the weak acid that is present in this first buffer. It's formic acid with a Ka value of 1.8 times 10 to the negative 4, so its pKa value would be the negative log of 1.8 times 10 to the negative 4. So pH equals pKa plus the log of the moles of base over the moles of acid. Well, this is all we know. We have the molarity of the sodium hydroxide that we are going to add in order to create our formic acid formate buffer. For every mole of sodium hydroxide that we add, we will convert 1 mole of formic acid into formate. We don't know the volume of sodium hydroxide that we're going to add, so we will define that as X. Then we go down to the denominator. We have originally, before adding the sodium hydroxide, a 0.2 molar formic acid solution. We want to prepare a total volume of 500 milliliters. So, if X is the volume of sodium hydroxide we're going to add, then 500 milliliters, or 0.5 liters, minus X will be the volume of formic acid we need to add, so that when summed together we get 500 milliliters. So this will be the original moles of formic acid before adding the sodium hydroxide. We will then subtract off the moles of sodium hydroxide added, because for every mole of sodium hydroxide added, we'll consume a mole of formic acid and create a mole of formate. So this is the setup. The rest is algebra. It is a little bit lengthy of an algebra problem, where what we will do first is try to consolidate what we have in the denominator after first calculating the negative log of 1.8 times 10 to the negative 14. Then I can move this over, and I'll get 0.5017. And then to get rid of the log, I need to take the anti-log of both sides, base 10, and that is just 10 to the, so 10 to the 0.5017 is 3.1746, and then 10 to this whole ratio is just the ratio. Now what I can do is take this entire denominator and multiply it by both sides of the equation. So I'm going to take this entire thing and multiply it by this. When I do that, I get this on the left-hand side, still equal to all that I have on my right-hand side is 2.0 times 10 to the x. Then I will collect my like terms, all my x terms and all my non-x terms, and I'll get this expression, and then divide both sides by 8.984, and x becomes 0.03534 sodium hydroxide. This is the liters of sodium hydroxide that I need to add. Well, what was the liters of the formic acid? Remember, it was 0.5 liters minus x. X we just calculated, so 0.5 liters minus x is going to be equal to 0.4647 liters of formic acid. So if I combine this volume of sodium hydroxide with this volume of formic acid, I should create 500 milliliters of a buffer solution with this as its pH.